Hello everyone, welcome to the third lecture of the series on AI using Python. In this lecture, we will discuss about regression and illustrate different types of regression problems. As we have already discussed in the first lecture, regression problem comes under the category of supervised learning. In supervised learning, the available data contains of input and output data, and our objective is to learn a model or a mathematical function that captures the relationship between the input and output. So in supervised learning, we are trying to fit a model or a function to the input-output data. Now, based on the nature of the output, supervised learning algorithms can be grouped as regression problems in which the outputs are continuous and can take any arbitrary value, and classification in which the outputs are discrete and can only have finite number of possibilities. Next, let's briefly discuss some terminologies that we are going to frequently use in the upcoming lectures. Firstly, the input sample or observation is denoted by small letter x, and the output sample or label is denoted by the small letter y. Now, the input data set or the input matrix is denoted by the capital letter X, and the output data set or the output matrix is denoted by the capital letter Y. So, the input matrix will contain the input samples as its elements, and the output matrix will contain the output samples as its elements. Now, in supervised learning, we can have different types of data sets such as training data, validation data, testing data, etc. So, we can use different terminologies for each of these data sets. We define the training input data as XTR and the training output data as YTR, the validation input data as XVA, and the validation output data as YVA, and the testing input data as XTS, and the testing output data as YTS. And finally, by univariate data, we means data set consists of observations of only one variable. And in the case of univariate data, each observation will be a scalar. Whereas multivariate data consists of observations of more than one variable. And in the case of multivariate data, each observation or sample will be a vector. As we have already discussed, in regression problems, the outputs or labels are continuous variables. Then our objective is to find a model or a function f which map the input to a continuous output. And the model can be represented as in this equation where f is the function or the model and x is the input variable and y hat is the predicted value of the output. Here p denotes the free parameters in the model, and our objective is to find the best values of these free parameters such that the predicted output y hat matches with the actual output or the testing output. Here, by learning the function or training the function, we means finding the best values of the free parameters p. And for that, we can use the available dataset, which consists of n observations of the input samples, which we denoted by x1, x2 up to xn, and also n observations of the output sample, which we denoted by y1, y2 up to yn. Now, the model f will be a function from the set R to the set R in the case of univariate regression, where R is the set of real numbers. And in the case of multivariate regression, f will be a function from the set Rn to Rm, where small letter n is the number of input variables and small letter m is the number of output variables. Note that here we are using capital N for denoting the number of observations in the data set, and small letter n for denoting number of variables in each input observation, and small letter m for denoting number of variables in each output observation. Now, based on the type of the function, regression algorithms can be grouped as linear regression, in which the function f is linear, and nonlinear regression, in which the function f is nonlinear. Next, we can give a brief illustration of linear regression using a simple example. And for that, first we will import the libraries NumPy and Matplotlib. And for illustrating linear regression, we will be generating the input-output data from a linear function. Here, the input data x consists of 100 equally spaced data points between -10 and 10, which are generated using the linspace function that we have already discussed in the previous lecture. Now, the output data is generated using a linear relationship defined as y is equal to ax plus b, where a is chosen as 3 and b is chosen as 2, which gives y as 3x plus 2. Here, we consider this model as the actual model, and this ys the actual output data which are normally unknown in practice. And in general, the available data contains noise or uncertainties. And to illustrate that, we will be adding some randomness in the model to generate the training data. Here, this RNG denotes random number generator, where we use the random state function in the NB library, which can be used for generating random numbers. Now, the training input XTR consists of 20 equally spaced data points between -10 and 10, and the training output YTR is defined as A into XTR plus B plus 2 into R, where R is the random variable. So here this len of XTR will be equal to 20. So this will be an array of size 20, where each element will be a random variable. So here we have A will be equal to 3 and B will be equal to 2. So YTR will be generated using the equation 3XTR plus 2 plus 2 into R. Now we can plot XTR versus YTR and X versus Y, which will give the plot as shown in this figure, where this red dot corresponding to the training data and this black line corresponding to the actual output data. Then in linear regression, our objective is to find a linear function or model for which the predicted output closely matches with this black line. For that, we can use the available data or the training data and use some algorithms to find the free parameters in the model, which are A and B in this case. Next, we move on to the illustration of nonlinear regression. And in that, we will be generating the data using a polynomial function. And here, the input X will consist of 100 equally spaced data points between -10 and 10. And the output Y is defined as A3 into X cube plus A2 into X square plus A1 into X plus B, where A3 is chosen as 0.02, A2 is 0.1, A1 is 0.5, and B is 2, which gives Y as 0.02 X cube plus 0.1 X square plus 0.5 X plus 2. And this we consider as the actual model, and here we have the model as a third order polynomial. Now, in order to generate the training data, we will be adding some randomness to this model. And for that, we will be using the random state function from the NB library, which can be used for generating random numbers. Now, the training input XTR consists of 20 equally spaced data points between -10 and 10. And the training output YTR will be generated using A3 into XTR cube plus A2 into XTR square plus A1 into XTR plus B plus R, where R is the random variable. Now we can plot XTR versus YTR and X versus Y, which will give the plot as shown in this figure, where this red dot corresponding to the training data and this black curve is corresponding to the actual output data. Now in nonlinear regression, our objective is to find a nonlinear curve which closely matches with this black curve. In the next lecture, we will be discussing how to find a linear model that fits the input-output data. And after that, we will discuss nonlinear models and nonlinear regression. That leads us to the end of this lecture. Thank you.